Alright, dear children of class 11 science, and now we do the last theoretical topic. It's an important law based on the emissive power and absorptive power of a body compared to the emissive power of the black body, perfect black body. And this law was formulated by Gustav Kirchhoff. Actually this is the name of the scientist who made an observation with the emissive power and absorptive power of a given body, ordinary body, with respect to the total emissive power or radiant energy produced by the perfect black body. And the law which was formulated by Gustav Kirchhoff is known as Kirchhoff's law. Now to understand this law, let me just write the statement of this law. And children, the statement says that the ratio of the emissive power to the absorptive power or for radiation of a given wavelength is same for all bodies at the same temperature and is equals to the emissive power of a perfectly black body at that temperature. Now to understand this statement, so let me just consider there's a body, and this is like a what body? Perfectly black body. Consider this is a perfectly black body. And you know, perfect black body are the good absorber of heat, and they are the good radiator of heat or the good emitter of heat. If a body absorbs all the amount of heat at different wavelength, then that body can also emit all the amount of heat at different wavelength. But this amount of heat which radiate can also be based on the temperature, and you learn even with the help of the law known as Wien's law also. Now suppose this is a perfect black body which emitting the energy, say at a particular temperature, say at temperature I consider say 5000 degree Kelvin, just taking an example. Now this perfect black body which emit radiation, and this energy emitted power, so the amount of energy, radiant energy emitted per unit area per second at this particular temperature is measured by the term known as power, emissive power. So the emissive power of a perfectly black body is measured by E, and this particular emissive power is measured say at a particular wavelength. So this is also very important, at a particular wavelength, and that wavelength I consider as lambda at the temperature T. And this emissive power is E lambda. So what is E lambda? Is the emissive power of the perfect black body at a given wavelength at a constant temperature. But if I take a body other than the perfect black body, so they can also absorb some amount of energy, they can also emit some amount of energy, although they are body which can transmit some amount of energy also. But let me just consider that if the transmission rate is very less compared to the absorptive and emissive rate for a body other than perfect black body, then that body, this is now for ordinary body. So I am using the word ordinary body, means not a perfectly black body. So if this is an ordinary body, then this body can this body can absorb the energy. This body can absorb the energy, and this body can even emit the or transmit the energy. We can use the word transmit the energy. So this body has a power called absorptive power, and this absorptive power is marked by letter A lambda. And this body has emissive power, and this emissive power is given by E lambda. So A lambda is the emissive power, and E lambda is the A lambda is the absorptive power, and E lambda is the emissive power of ordinary body. And this absorptive power and emissive power is at a given wavelength at a constant temperature, and even I consider the temperature is also 5000 Kelvin. But you take ordinary body of any shape, of any material, and all. But as for the Kirchhoff's law says that the ratio of the power? Emissive power. The ratio of emissive power means E lambda to the absorptive power means A lambda. A lambda for radiation of a given wavelength. Is same for all bodies. All bodies at a constant temperature. And that temperature I consider say 5000 Kelvin. And this ratio is also equals to the emissive power of a perfectly black body at that wavelength at that temperature. So E lambda by A lambda is equals to E lambda, capital E lambda. So this is the mathematical relation or statement of what Kirchhoff's law. But this ratio is always constant. Children, this is very important. This is always what? Constant. Okay, now this is true for all materials of a body at a particular temperature and at a given wavelength. Okay, now out here, the same relation I can write this as the ratio of E lambda by A lambda with 1 equals to E lambda by A lambda equals with 2 equals to E lambda by A lambda with respect to 3. It will go on and is always equals to capital E lambda. And this is for what? Perfect black body. Now out here 1, 2, 3 actually represent different surfaces of different bodies. Okay. Now thus at a definite temperature and for a given wavelength, the ratio of the emissive power to the absorptive power for different surfaces is always what? Same. Always what? Same. Now if the surface, I consider say there is a surface say A. Let me consider this is a surface what? A, and there is another surface say like B. Now if a surface A radiate say 10 times more energy than surface B, then at the same wavelength surface A absorb 10 times more energy than what? Surface B also. Means if there are two surfaces A and B which radiate energy, okay, in different way, but I mean to say like if surface A radiate energy 10 times than surface B, okay, at a given what? At the same wavelength, okay, at a particular temperature, okay, then surface B also emit what? The surface A also absorb, surface A also absorb 10 times more energy than what? Surface B at same wavelength at that temperature. So this is the statement of Kirchhoff's law. Now the next part that is also very important is that the importance of Kirchhoff's law is that a conclusion can be drawn is that if the surface is a good absorber at a particular wavelength of radiation, if a surface is a good absorber of a particular wavelength of radiation, then that surface is also a good emitter of that wavelength of radiation. That's why I gave you the example out here like there are surface A and surface B. Okay, now you can see in these two example also, surface A, as I said, radiate 10 times more energy than surface B. Then at the same wavelength, surface A also absorb 10 times more energy than surface B. Because if it is a good emitter, this is also a good absorber. If it emits 10 times more energy than surface B, then this surface A also absorb 10 times more energy than surface B. Okay. And this particular fact can also be observed in our day-to-day life. Now children, we know that the red glass appears red in white light. Red glass appears red in what light? White light. Because it reflects red light and absorb what? The rest of the light. Since the average effect of the rest of the what light, that means white to red, okay, is greenish. Which is the what? Greenish. So we can say that the red glass absorbs green light strongly. Red light glass absorbs what? Green light what? Strongly. So hence, according to Kirchhoff's law, if you see, the emissive power of red glass should be minimum for green light. Sorry, not minimum, sorry, it should be maximum because of the wavelength. Okay, it should be maximum for what? Green light. That's why you know that when red glass is heated to a high temperature, light gives greenish glow on being heated. So this is simple observation that we can see in our day-to-day life. But this observation or conclusion that I explained just now is nothing but based on which law? Kirchhoff's law. Okay, so this is the importance of what? Kirchhoff's law. But most important part out there is what is the statement of Kirchhoff's law and how we state the law, that is important. So I have explained in detail about the Kirchhoff's law. Now there are few numericals that we need to solve from this chapter, so then your chapter get completed. So we'll start new chapter also. Thank you so much.